Okay, I'd like to welcome you all. My name is Steve Skeena. This is supposed to be CSE373, the analysis of algorithms. And I'd like to welcome you all to the class. I'm going to start out by going over the syllabus. So everybody in the back of the room there and on the course website, if you don't have it now, I've made available a course syllabus. I want to start off today's lecture by going through all the rules and policies of what we're going to do in here. And then hopefully we'll get into start getting into some fresh material. Any questions about what we're going to do or how we're going to proceed? I assume the class runs. This is the algorithms class. It will run from 1 till 2:20, and I'm going to find 1 o'clock as being exactly the time on that clock. So that's when I'm going to sort of start every day at the second it hits 1. My office is in the computer science building. I have office hours on Tuesday and Thursdays from 9 a.m. till 10:30. So good times to talk to me are in the morning on Tuesday and Thursday, or if you come by, talk to me after class is actually a very good time. If not, if you need to see me, you can send me an email and we can try to work something out. We are blessed this semester, and I'm going to say blessed, okay, with 2 TAs who I think are going to be very good this time. They're experienced graduate students. They know a fair amount of algorithms. So I'd like to introduce our TAs, okay. Haji and Jayla, stand up, okay. First, a round of applause for Haji and Jayla. Okay, good. So I will post their exact office hour detail on the website after this is done. But I want to do a quick survey here. Haji is telling me that his office hours are going to be on Wednesday between 4 o'clock and 5:30. Who has a class Wednesday between 4 o'clock and 5:30? Some, but not everybody. How many people here have classes Thursday between 4 o'clock and 5:30? Some people, but maybe a different set of hands. Okay? Let's now go on. Jayla says she's going to have her office hours Monday and Wednesday from 1 to 2:30. Who has off class during Jayla's time? Who, now that everybody's looked at this, who here has classes during all of the TA's times? Okay? Then you people are going to get to know me after class if you want. Okay? I think that sounds like enough coverage of classes that I think we'll probably stick with those office hours. And if we have problems, let me know. Okay, so I will post on the website what the office hours are. But for now, and where they will be, but that's probably going to be what we're going to assume. Any questions about office hours or anything like that? Okay, let's go through the rest of the stuff. First thing I'd like to say is the textbook for this course is called the Algorithm Design Manual. I think it's a very good book. Okay? And of course, I should think it that way because I'm the one that wrote it. But a lot of other people also think it's a good book. One thing that I want to encourage people to do is to actually read it. Okay? That sometimes, obviously, my lectures cover a lot of the same grounds because, I'm the same person that wrote the book. But I do think that reading through and thinking about this stuff carefully is actually an important thing. And I think that, sometimes people have not read the book as carefully as I would like to see people do. So one thing to note in the syllabus is on the last page of the syllabus, I give a lecture schedule. I also give a column there about what pages, the reading, what are the pages in the book that correspond to that lecture. And I do encourage people to read it. I think I wrote it in a way I want it to be a readable book, and I do think that thinking about these things deeply and seeing the traps you fall into is different than just listening to me glibly do it in class. So please read the book, and anybody who wants me to autograph their copies, I'm happy to do so. Okay, any questions about the textbook? Okay? Some of you may read the book, decide it's a terrible book and you don't like it. There are lots of other algorithms books out there, okay? And if you find that you learn better from some of those, God bless you, okay? Any questions about that? Okay? Good. As far as the coursework goes, as far as the grading goes, My grade distribution here is going to be based on the following thing. 5% of the grade will be based on daily problems. You should have picked up at the top of the room 2 handouts today. One was the syllabus. The other was the daily problems. Every day, starting next class, I'm going to start every lecture by going over a daily problem. If you don't have it, you can sit down. It's on the web. It'll be there afterwards. You don't have to get up and do it. But every lecture, I'm going to start by going over the daily problem. And what your job is before class, you have to work on the daily problem. Turn in a paper, 1 sheet of paper with what your work is on the daily problem. And we will be counting what the, basically we will be counting how many daily problems people turn in over the course of the semester. That is the grade under the daily problem assignment. Yes? Okay, does it matter if it's typed or written out? For the daily problem, what matters most is that your name be on it. Okay, we are not going to grade the daily problems. And so some of you may snicker around and say, hey, that's great. I just write my name on the sheet of paper and I turn it in and that's fine. And you're right, okay? But the daily problems are, I think, very important because I think that they work best if you have spent some time trying to think about the problem that we're trying to solve. Algorithms turns out to be a problem where solving these problems requires thinking in the right way. Okay? And you think in the wrong way, you will stare at it forever and you will never get it right. Okay? But learning how to think in the right way is a hard thing. Okay? And it takes practice and it takes trying to do things and seeing where the traps are. Okay? And you learn, I think you will discover the traps in many cases by you think about one of these daily problems. You then see me go over it in class and you'll suddenly see that what you did was not right. Okay? Or you got stuck on the daily problem. But thinking about these things is how you actually learn this stuff, okay? And so I strongly encourage people to go and think about the daily problem before class. Spend 5 minutes, 10 minutes, 15 minutes trying to do it. Come in, turn a thing in something with your name on it, okay? That will be fine. But just the exercise of thinking about this stuff will warm you up greatly for being able to do this. Any questions about the daily problems? Every year I do a little study for myself at the end of the year and take a look and correlate the number of problems people turned in with what the grades on the midterms and the final are. And there's always an amazingly good correlation, okay? Because the people who look at this stuff, who think about it a little bit, it warms them up to being able to do this stuff. And when I go and show you the solution, it's not like, oh, he's from Mars. Where did this come from? It's like you'll see, oh, I see, I tried to do it this way, and then that's where I hit my problem. Any questions about that? So I do encourage you to do those and take those seriously. That's an important thing. There will be a total of 5 homework assignments in here. These homework assignments will be given out every 2 weeks-ish, okay? They will have about, let's say 5 to 10-ish problems on it. And these will be graded for content. So it's not enough to just write your name on, okay? But these are also important for learning how to, to solve problems and stuff like in here. There's going to be 4 of these problems. 4 of the 5 homework sets I'm going to let you do in pairs, okay? Meaning I encourage you to find a course buddy who is going to be your homework partner, okay? And again, in solving homework algorithm problems are about ideas. And I find that it is best when you're working on an algorithm problem to be arguing with somebody else about what, oh my God, how do we do this thing? Can we do this? No, that's a dumb idea, okay, because of this reason. And so I encourage people to do in pairs. Each pair is going to turn in 1 copy of the homework between them. And both people who are on the assignment will get the same credit. Any questions about that? So over the next couple of days, I encourage you to try to figure out who your partner should be. Okay? If you can't find a partner, I will set people up with partners. But I don't want to ever hear what a louse your partner is. If your partner doesn't do any work or something like that, then just leave your partner. Okay? I don't want to hear complaints. I won't be a marriage broker between you and your partner. Any questions about that? Okay, good. The bulk of the grade in here is going to be on midterms and exams. There's going to be 2 midterms, and there's going to be a final exam. They're both going to be made of problems like the homework, okay? Most of the problems on the exam will in fact be exercises from the book. So one way to study for the exam, that's a good thing to do, is to look at the whole exercises in the book, okay? Maybe the ones that weren't assigned, okay? And go through and do those and think about them, okay? And that is, I think, a great way to study for the exams, because that's sort of what the exams are going to be like. Any questions about that? We'll talk more about the exams as the midterms as it gets closer. Any questions about the grading? So that is the distribution of what I will use for weights on assigning the different things. I will then grade on a curve and make cutoffs where I think I should make cutoffs. Any questions about grading? Okay, good. Let's keep moving on. I said that there were going to be 5 homeworks, and I said 4 of them were to be done in teams. One homework, which is homework 4, is kind of an interesting thing. Algorithms is about trying to design fast ways of solving problems, fast procedures for getting computers to solve problems in some sense. That's basically what the subject's about. For one of our homework assignments, we're going to have a programming assignment where it is basically a race situation. There's going to be an algorithm problem. I'm going to ask everybody in here to write a program using backtracking to solve this problem. Okay? You will be graded based on how fast your program is. Okay? The fastest program in the class wins a prize. The slowest program in the class also wins a prize. But that one you guys don't want. Okay? But that one is going to be so that's going to be homework 4. That one you won't be working in teams, but otherwise you'll be working in teams. Any questions about that? Yes? How do I break ties? I break ties how I feel I should break ties. We'll break ties when we we'll talk about the programming contest. We'll talk about that then. Okay? So actually, I guess the real answer is I will run this thing until it's not a tie, and I know I can separate them. So these things usually don't end up as ties. Any questions? Okay, let's keep going through the syllabus. Like I said, the exams in here are going to be based on typically homework problems from the book. Okay? So that's the right way to study. In past years, I've occasionally promised that all the questions on the midterms and the final will be from the book. Okay? I'm not making that promise, but a lot of them are, and so it's still a good way to study. But I am going to be trying to bring some other fresh problems into the mix. Okay? What else can I say? Going through the rules of the game. This semester, the lecture is being recorded. If everything is right, that camera up there, okay, seeing up there, right over there, that camera should now be turned on and is recording what I am saying here. Hopefully this microphone is working, and that means that everything would be recorded. And this would mean that somehow over the solar system, okay, or Blackboard, over Blackboard, you guys should be able to get the lecture videos after the class is done. If anybody actually succeeds in doing this, let me know. I want to be convinced that this process is working. So the good thing is we're going to be recording. So if, let's say, you have to miss a class, you can go and catch up on it, hopefully, over the recorded video. That's a good thing. If for some reason you want, I have videos of past courses I have taught available on YouTube and my webpage. If you really want to watch an old videos, that's fine, okay? But I do encourage you to, if you need to, watch this year's videos, okay? And even more, I encourage you to come to class because you're paying for a live performance. And it's a lot easier if you can ask questions and things like that. Any questions about the recording? Okay? So if there's anybody who's absolutely allergic to possibly being caught on that camera, make sure you don't sit in view of that camera. Any questions about that? Okay, good. What else do I say in here? I have a course webpage at www.cs.SUNYSB.SKIENA, S-K-I-E-N-A 373. There you'll find all the handouts. So in case you didn't pick up one of the handouts, like the daily problems or something like that, pick it up there. Okay? Any questions about that? And if there's any announcements, that's how I will communicate with you. Again, you guys should do homework problems. Do them in pairs for the homework assignments. Daily problems you do originally. Daily problems are due at the beginning of class. You know, at 1 o'clock, the moment the 1 o'clock thing happens there, what I'm going to do is dramatically put my coat over all the homeworks that had been turned in so far. So nobody can turn in a daily problem after the clock hits 1. Okay? Any questions about that? Okay? Again, what else do I want to say? I have one other policy on my homework problems that people tend to like. I know people get busy and they have jams with other classes and things like that. One of my homeworks you're allowed to turn in late. So there's 5 homeworks. You're allowed to turn one of them in up to a week late. Okay? I don't encourage you to make it the first one. Okay? I don't encourage you to have to use this. Okay? But if you get into a bind, you don't have to tell me and beg, oh, my dog died, something like this. Okay? You get 1 free extension. Turn in your homework within a week. Right on the top, this is my free extension. Okay? But you don't get 2. Okay? Any questions about that? Okay? So that settles that issue. What else do I sort of say? As far as other announcements goes, there's some boilerplate announcements. One is that if you have a physical disability, a physical or a mental disability or learning disability, something like this, you should be aware that there is a Disabled Student Support Services Center. I have taught courses once where I taught for half the semester. At one point, the student came to me and informed me he was deaf, okay, and hadn't heard anything I had said all semester. And so there are people, you know, who have issues and stuff like that. You should be aware of the Disabled Student Services Center, okay? If you are, register with them if you need it. If you don't need it, obviously it doesn't matter. Any questions about that? Yeah.
Sorry about that.
Okay, what about the course?
On the course webpage, where are the homework posted?
The homework should be, okay, I haven't given out any homework, so there aren't any homeworks up there. The daily assignments, there should be a link there that says daily problems, okay? Look at that. If you can't find it, send me mail. Any questions about that? Okay, fair enough. What else do I say? Again, there has to be no cheating in here. Now, what are ways to cheat? Daily problems you can't really cheat on because you're allowed to just do whatever you want before class to turn it in. The problems, the homework assignments, it's got to be you and your partner, okay? But that's perfectly fine, okay? And again, that's what I'm not really worried about. Things about the exams are usually the best way people get caught cheating in here. So again, when it comes to exams, you can't look at other students' papers. One student, 2 times ago, I caught somebody doing that, and that person got expelled, okay? So make sure when you do the exams, you do your own work and stuff like that. If there is going to be any kind of academic problems, dishonesty things, I will take it through the normal procedures. The procedures are listed on the syllabus. Any questions about that? What else do I sort of say? Basically, I would like to, again, it's a big class. I actually like teaching to a big class. And I like it to be interactive, so I do hope there will be a lot of questions in here. And again, I hope I will get a chance to get to know you guys. You can come to office hours. I also hope to have a pizza with the prof with some students, okay, midway through the semester. If I haven't made any statements about that, somebody come here and remind me about midway through the semester, and I'll make sure I do that. Any questions about that? Okay, any questions about the organization of the course before we go into some real material? Okay, yes? Is it possible I will give you a 10-minute leeway on the daily problems? The answer is no, okay? Let me explain why, okay? Because what happens is when I start the class, okay, there will be a mad rush for people trying to desperately get their daily problem in, okay? Then if people are continuing to come up here, it's very distracting to other students turning it in. The stakes on the daily problems, if you do the math, are actually quite low, okay? It is 5% of your grade divided by 28 problems. That's the course value of each problem, okay? And there has never been a student that has failed because I didn't record one of their daily problems, okay? So try to get it in on time, okay? And that's the way we have to do it. Any questions about that? Okay, yes?
A question about program
Okay. So what I do say is that that on another thing that, let's say, people can do, which if they want, this is for a very, very small amount of extra credit. I encourage people to solve a certain number of these programming contest problems that I make available on the Programming Contest Judge. If you go to the course webpage, I think that will be clear. Very few people from this course actually end up doing it. Okay? The amount of credit I will give you is going to be so low, it should be due because you do it because of interest and not because of greed. But if you're interested in these kind of algorithmic programming problems, the kind of thing that happens on the ACM programming contest, I sort of encourage you to play around with that. And if the course is not set up there, send me mail and I will make sure I get that set up. Any questions about that? Okay, any other logistical things before we go into the real course material? Okay, good. So let's see if we can go here. How do I move forward? Is this good? Bingo. Okay, so this is a course on algorithms. And so let's see, so what is an algorithm? Okay? As far as I am concerned, an algorithm is, they come up various catchy ways to say things. I think of the algorithm as somehow the idea behind the computer program. Okay? Typically, you have a program that wants to get something done. Okay? The way you express it getting done is in that programming language. But on the other hand, the way the procedure for doing it is the algorithm. Okay? So another catchy way of saying it is that I once liked was that an algorithm is the thing that stays the same about a program. If it's written in Pascal, okay, on a Cray supercomputer in New York, or maybe in Python on a PC in Stony Brook, okay, it's something that doesn't. It's a part of the program that doesn't change when you write it in a different language. That's another way to say it, okay. And algorithms, to be interesting, they have to solve problems that are well-defined problems. And they have to solve them in a correct way that works on everything. So let's look at what we mean by a problem. When we talk about a problem in here, we are not going to be talking about a specific data set or anything like that, or a data file. Okay? When we talk about a problem, we are talking about a specification of allowable inputs, okay, and a specification of what you want done with each of those inputs. So sorting is the classical algorithm problem. How many people here have seen sorting in one of their classes? How many people have seen sorting in 2 of their classes? 3 of their classes? 4 of their classes? People still raising their hands. Well, it's going to be 1 more after this semester, okay? But sorting is a classic algorithm problem, okay? And what is sorting, okay? It's specified by what the inputs are, okay, a sequence of all the numbers. You're given n numbers in some arbitrary order. And the output is you have to permute them. You have to, reorder these things so that they are in increasing order, okay? So A2 is greater than A1, A3 is greater than A2, ... Okay? Specified like this is an algorithmic problem. And the goal here for us, when we try to solve it, is to find a procedure that will work to always take any input and transform it into the illegal output as efficiently as possible. Any questions about that? That is our big picture goal. And again, our goal is that we want to do things efficiently, meaning it takes very little computer time, but we also want to do things correctly. We want to make sure that our algorithm always works regardless of what the input is. Any questions about that? Okay, that may seem obvious. Now, the idea of correctness being obvious, I'm not going to spend as much time over the whole semester talking about correctness as I should, but here's where I guess I want everyone to start listening, okay? An algorithm, to be a real algorithm, okay, it has to be correct. What does it correct mean? It means that on every possible input, it always achieves the desired output, okay, as specified, okay? That means that it's always got to work on all possible legal inputs. More to the point, if a specification of a problem says return me the solution with the lowest score or the highest value or something like that, it's always got to return exactly the one with the highest value or the lowest cost, okay? Often in here we're going to see, in fact starting in a few minutes we're going to see, it's very, very easy sometimes to define procedures to solve problems that give you answers that aren't always exactly the right answer. And we know what we call an algorithm that doesn't always return exactly the right answer? There's a technical term for that kind of an algorithm. Yeah? You say it's a heuristic, and here I say it's wrong. Okay? That's the important thing here. Okay? A heuristic is a procedure that sort of kind of does something. In here we're going to be interested in algorithms that always return the right answer. Okay? And this is a very important distinction that isn't immediately obvious to people. Okay? You may say, yeah, I know programs can be wrong. You're used to thinking about programs being wrong. And what do you do when you have a programming assignment and your program is wrong? What do? You change something and you run it again and you hope it's right, right? In that case, the program is wrong but fixable, okay? Usually, algorithms, when they're wrong, are not necessarily fixable. And I want to make clear that this is true, okay? So let's start to talk in here about a serious, a kind of important algorithm problem, okay? Which is a problem that I know I encountered once. I was visiting a consulting company. I was visiting a company that was in the robot testing, in the printed circuit board testing business. And have any of you ever dropped your iPhone and broken it? Okay? If you open it up, you'll see in there is going to be a circuit board. Okay? And on the back of the circuit board, there are going to be there's parts that are attached to this circuit board. And on the back of the circuit board, there are connections that a machine had to solder, okay, to attach the component to the printed circuit board. How many people know what I'm talking about? Raise your hand if you know what I'm talking about. How many people don't know what I'm talking about? Still a sizable number, okay? Let's see if this helps. If you look at the back of your printed circuit board, okay, you will probably see something that looks like this, okay? Actually, where did I have? Supposedly here I've got a pen. Okay. This will work about half the time in my experience, okay, what I'm about to do now with the drawing of things. So let's see if we're going to get this working. No, looks like we're not. Okay, let's try this. Okay, maybe we'll already abandon this technology for the semester. Hold on. Okay, so much for this technology. Okay, so what do we have here? Maybe we'll have to go to the board then. So what is this supposed to be? If you take a look at a circuit board, on the back of the circuit board, you will see a bunch of holes like that. Does everybody kind of get this idea? These are places where, if you look at the reverse of the thing, a integrated circuit got pushed through the board, and the integrated circuit has the wires on it, the connections of where all the electricity is supposed to flow. You need to attach the part to the board, okay? And the way they do that is with a technology called soldering. Okay, we take some metal and you melt it over there, and it makes an electrical connection. So any company that is doing manufacturing with printed circuit boards is going to have to program a robot to visit from one location to another, soldering all the things on the back of the circuit board. Okay? And this is a part of any reasonable manufacturing these days. Any questions about that? So there exists these robots, and to program them, they're going to be making 1 million iPhones, okay? Every iPhone has the same layout of pins in the back of the board, okay? They have to program the robot to solder every pin on the board, and for efficiency, they want to do it using as little time as possible, okay? So imagine the situation is you've got a robot that can be programmed to move from any one geographic position to every other one, okay? And once it gets to that point, it does a bzzzt, and the solder is done, okay? What is the way that we would like to program the robot so that the boards get tested quickly, okay? Would it be a good thing for my robot to program it to go, bzzzt, 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 okay? Or might there be a faster way? Okay? What is the problem with the order that I was jumping through? Okay? Yeah?
Well, part of the problem is there's this implicit power
Well, you say the solder lines don't cross here. That's actually not really a case here. Okay, that actually is not. The solder's on the other side. So I'm going to say I don't. That is not the issue. The issue should be one of what? Yeah. I'm wasting energy, or forget energy. I'm wasting time. Okay, the robot arm takes time to move, right? The longer it moves, the longer it takes to test the board, right? So if you want to program one of these devices to do the soldering, you have to take as input the arrangement of pins on the back of the board, and design an order to visit all those pins, one at a time, so that you get back eventually to the original spot, visited all the pins, and the cost of doing this is minimized, meaning the total distance that the robot arm traveled is minimized. Does everybody see that this is now the problem that these people face? Okay? Given an arrangement of pins based on the particular device they're manufacturing, find an order to visit all the pins so that you minimize the total amount of distance traveled. How many people does this problem make sense? Does this problem make sense to you? Raise your hand. Okay, how many people doesn't it make sense to? Okay, good. Okay? So, boom. So let's think about this. Can you now give me an algorithm to, given the positions of a set of endpoints, try to figure out what is the minimum number, what is the ordering of those points, so as to minimize the distance traveled? Okay? See what my problem is? I am programming the robot. My input is I've got n of these distances. Okay? And I want to try to find the ordering that minimizes the travel. Any ideas how I can go about doing it? Can anybody suggest a procedure, okay, or something that might help me? Yes? You're saying I can use Dijkstra's algorithm to find shortest path. Well, let's think what that means. Dijkstra's algorithm, for some of you who may know, is a way for given a network to try to find the shortest path between 2 points. Now, is there a connection between this problem and that problem? See, some people say yes. Some people are saying no. Okay, I say not really. Why is that? Because here I am forced to visit every point on the board, right? Dijkstra's algorithm asks to find the shortest path between here and there, right? In an ideal world, there's no other point I have to visit. In fact, if this was the distances here were as the crow flies distance, the shortest path between one point and another point is going to involve exactly 0 intermediate points, right? So it's a problem that smells a little bit like shortest path in a graph, but it is not shortest path in a graph. Yes? Okay, we don't want to say that yet, okay? But let's think a little bit about it fresh. Again, some of you look ahead, you know what the name of the problem is. But let's think about what kind of procedures might solve this problem. Okay, yes? Okay, so now what you're saying is, again, you guys are working backwards. Usually people work forwards, okay? But let's take a look at that. We agree that this problem is a famous problem called traveling salesman, which I'll talk about in a little bit. We agree we could search through all possibilities in this. In fact, ka-chunk, 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 okay? We could go through and try all possible orderings of the points. If there's n points here to be searched that we're looking for, if we give each of them a name from 1 to n, how many of different orderings are there of these n points? You say n factorial, it's not quite n factorial. Well, -1 or something. What is it exactly? Okay? So how many different orderings are there? How many circular orderings here are there of n points? We agree that if we had a linear ordering where we started from 1 and went to the nth point, there are n factorial different permutations. So what do we know? There's a couple of different issues. One is there's n factorial. You're saying backwards is the same as forwards for the robot. So that's an interesting observation, right? The visiting from points 1 through n, getting back there, is for the robot the same as going from n back to 1, right? That would suggest n factorial over 2, right? There's something else going on, though, yeah. So it's n minus 1 factorial over 2 because it's a closed loop. Does everybody see the robot has a closed loop? So it doesn't really have a starting point. You might as well assume it starts at point 1, okay, and then goes through a permutation of all the other n minus 1 points, right, before getting back to 1, okay? So that's an argument that there's something like n factorial or n minus 1 factorial, or probably the right way answer might be n minus 1 factorial over 2, different tours. We could systematically construct them. And then what would happen? It would take forever, okay? Because by the time you get to 20 points or so, okay, what's n minus 1 factorial over 2? N minus 1, for 20, n minus 1 factorial is 19 factorial. Anybody have a calculator? 19 factorial is going to be an ungodly number. You divide it by 2, it is still an ungodly number, okay? Any computer there is not a computer on Earth during the rest of recorded history that will be able to go through 19 factorial things, okay? So if we want to find the optimal tour, we can't do it by exhaustive search, okay? Any questions about that? That's an example of, if we try all possibilities and pick the best one, that is going to be a correct algorithm. But we agree it's not going to be an efficient one, okay? Any other ideas for a more efficient way of doing this thing? And again, I'm a little bit afraid that I've, by moving around these slides, I've tipped my hand a little bit. But can anybody come up with other procedures for solving this that might work? Yeah. Okay, so what he's now suggesting is a different idea, which is not one that I even have on my slide, but let's talk about it, since I can't write on here very well. What he is suggesting is that and maybe I'm trying to decide if I want to go here or not. You take a look at your points. You find something called the minimum spanning tree, which we'll talk about during the course of the class. If you don't know what it is, don't worry about it. If you don't know what it is at the end of the class, do worry about it. Okay? And use that to guide your search. Okay? And what I will tell you is that can produce a wrong solution. Okay? And let me sort of argue why that might be. And let's see if I can do that on my head. Suppose we have our points arranged in a raindrop flow like this, okay? What you're going to do, what is the optimal traveling salesman tour on this set of points? Okay, can anybody, let's say, well, let's give them numbers. 1, 2, 3, 4, 5, 6, and 7. What would be the optimal ordering here, yeah? 1? Well, it's in let's say these are geometric. These are on a circle, so these are equally dispersed. Probably what you're saying, go to the closest one. And let's say, I'm saying this is probably going to be the optimal tour. Does everybody kind of get that idea? Now he's saying, let's use a minimum spanning tree to guide this tour, the order in which we're going to be visiting the points. In this particular instance, if we have enough of these points on the outside, if we have few enough points on the outside relative to this distance is going to be big relative to these distances, okay? The minimum spanning tree is going to look like this, okay? And if it looks like this, he's going to suggest an ordering that basically uses the order of the minimum spanning tree. The order of the minimum spanning tree doesn't really give you much information. In particular, an ordering like this would be just as good as far as the minimum spanning tree is as the ordering where we go around the outside in a reasonable way. Okay? I don't know how many people are following this. This is not where I normally like to go, so I think it's a little deeper than I like to go right now. How many people are not following me? Few who will admit it, okay? Bottom line is, there is another fancy way to try to come close to a traveling salesman tour that he's suggesting. But what I think I have just argued is, that if we use the procedure he's saying, it's not always going to give us the right answer. There is going to be an example here, which I think some of you understand, as to why this is going to give you a wrong answer. Okay? Any questions about that? But let's look at something, okay, any questions? Let's look at some other procedures, though, which usually are the ones students come in and suggest, okay? And let's look at why they are right or wrong. One idea that people usually come up with is what they would call nearest neighbor search. You start with one point. You know you're going to have to visit one point to solder. You go to the point that is closest to it, right? And now you get another tour. You get another link in your tour, right? You then go from this new point and find the unused point that is closest to it, okay? And keep visiting the nearest neighbor until you run out of points, okay? How many people see what I mean by this algorithm? Okay? So if we went back to this particular example, again, I'm at this moment feeling that I'm not getting, let's see if I can get any color out of this. Again, as always, I'm not giving color here. Okay, so again, what I would probably do is start from this point. Visit the nearest neighbor, which would be this one. The next nearest neighbor might be this one. The next nearest neighbor might be, let's say, this one. The nearest one to that might be this, but that's already used. Keep walking, and in each round, visit another point that is closest to the one that you're currently at, okay, that you haven't used yet, okay? Any questions about that procedure? Yeah. How does it know which point to start? Well, there are a couple answers I can give. One is maybe it doesn't matter, because eventually you're going to have to get back to where you start. Or if you think it does matter, try all of them. Start from one, go compute the nearest neighbor tour, then try a different one. Compute the nearest neighbor tour from that, right? And pick the best one. Now, these are reasonable algorithms. This is sort of a nice code for it, right? You start, you pick an initial point. While there's an unvisited point, pick the closest nearest one. And then keep repeating until everything's done. Yeah? So the trouble is we don't know that this is correct, okay? In fact, I want to argue with you that this is not correct, okay? What is my example of points here? My example of points here is here I've got 1.0. I've got a distance 1 away to the left, 1 away to the right. Here I've got one that is a total of 2, okay. So each one of these numbers represents the x-coordinate of a point on a line. Suppose all the points that I'm soldering are on a line, okay? In this case, they go from that point at 21, minus 21, to 11. What is the optimal tour for this particular point? If you could program the robot, what's the optimal way to go it? I've seen a lot of people saying things like this, right? You start from the left, you would go beep, 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 and then go back, right? No wasted motion. What happens, however, if you start the nearest neighbor tour from this position? You've got one point, your nearest neighbor is either one to the left or one to the right, okay? Suppose you it's now a tie, right? Which one should you pick? Well, let's say you pick this one over here and you go to the right. Now if you look at this, you've got another point here that is 2 to the right of it, right, from 3 to 1. And you've got another unvisited point that is 2 to the left of it. Does everybody see that? So which one of these should you pick? Well, you don't know, right? Maybe it doesn't matter. Maybe I'll pick this one. And if you look, I've cleverly set up this points where every time you go through your nearest neighbor business, you've got 2 points equally spaced. Does everybody see that? And so if you do this, okay, you're going to zigzag back and forth in your tour, obviously wasting time over the direct thing. Okay? Any questions about that? Okay? Yes?
What if you started
Okay, so he's now suggesting a modification to this, and I will tell you it won't work. Okay, I didn't necessarily understand what you're saying, but I know it doesn't work. Okay, now why don't I know that it doesn't work? Okay, so what is the situation here? Okay, before we get into this, okay, there's some cutesy things here. Does everybody see this example? I want this to be an important example here. In the course of designing algorithms in this class, fairly often you guys are going to want to say, oh, why don't we try this? And you're going to suggest a procedure sort of like this, a greedy, we call it a greedy procedure. Always take the best next move that looks best to you. Okay? And you will say this is an algorithm. Unless you can prove that this always gives you the correct answer, okay, presumably your algorithm is wrong. Okay? Any questions about that? Okay, yes. Yes. So why does it need to be a closed loop? Okay, that's a good question. Okay, so in what you might be saying here is that in the printed circuit board testing thing, maybe there is no reason why you have to actually go back to a closed loop, right? You're not going to solder that point again. If you feel you need, let's say if there was one place in there that was needed, let's say to dip the rod to keep it clean. Sometimes there's a cleaning point, okay, and so that would be my excuse for why it might have to be closed. But if you don't close it, it turns out the problem doesn't change very much. The problem of finding a tour for doing this turns out to be no easier if you don't require it to be closed, just if you require it to visit every point. Okay? Any questions about that? Okay? So let's just remember the big picture here. Again, you guys have gotten me a little out of order, which is good, because I like that this is an interactive thing. But let's keep track of what the big picture is here. There are algorithm problems. There are natural procedures to try to solve those algorithm problems, typically saying always do the best next thing, that always seem like they're going to always give you the best possible solution. In general, they don't. Okay? And you have to be able to either prove that your algorithm does give you always the best solution, or you've got to have the wherewithal to try to look for examples where it will be wrong. Okay? Any questions? Okay? Let's just look at maybe one example of this. Look at this particular example here. We agreed that the greedy algorithm, nearest neighbor, where you start from a particular point, okay, can give you the wrong answer. Can anybody argue that starting from the leftmost point might, in doing the greedy algorithm, doesn't always work? Okay, let me now try some modification to it. Notice that with this problem, if I started on the leftmost point, okay, and I say nearest neighbor, nearest neighbor, nearest neighbor, nearest neighbor, I'm going to get that one right? Does the nearest neighbor algorithm always work when I restrict it to the leftmost point? Okay. Can anyone give me a counterexample? Yeah? What if everybody turns their head 90 degrees? Okay. And now they're all equally to the left. Does everybody see that? And even if I nudge this one a tiny bit more, I can even break the tide and nudge this one out and make you pick it, right? And it's not going to, it's still going to give a wrong answer. Okay? Any questions about that? So what's interesting here? Again, this problem, I'm not going to talk about that other heuristic because we've gone into it a little bit deeper. But what is the interesting point here? We have a problem where there is no fast algorithm we could find that was correct. There was a slow algorithm based on exhaustive search that was correct. There was no algorithm we found that was fast and correct. And the reason I could dismiss one of his algorithms without thinking about it is, as we will see at the end of the semester, there is a good reason to believe that no fast algorithm that's always correct for this problem exists at all. Okay? This is a problem that is known as many of you seem to have found out, the traveling salesman problem. As the story goes, why do they call it the traveling salesman problem? You have a salesman that has to visit a bunch of different cities to make sales calls. They want to start at home. They want to end up at home, so it is a closed loop. Okay? And there is a cost from traveling between one city and another city. How should the salesman schedule his visits? At the cheapest cost, so he visits all the cities. That is the traveling salesman problem. By another name, it's the problem that we were just trying to solve. Okay? And it's a well-known example of what we will call an NP-complete problem. A problem for which there is no fast algorithm, no matter how clever you are. Okay? And we will talk about that at the end of the semester. Any questions about that? Actually, one thing I didn't do when I was going through the course handouts was review what we were actually going to be doing this semester. Maybe that's a good point to try to do. What is the basic flow of the semester going to be? We're going to start out for the first 3 lectures or so talking about preliminaries for the course. What is an algorithm? How do we measure, how do we talk about efficiency? That's where we get into this notion of the big O notation. What other mathematics are important? Things like logarithms and other things that we're going to need for analysis of these things. After that, we're going to have a unit on data structures, because we're going to find that the key to making a lot of procedures run fast is using the right data structure. Now, some people are in here have not taken CSE373. Are there any computer science majors in here who have not taken CSE373? Okay, or the equivalent version for the honor students? Okay, 214, the data structures course, is a prerequisite here. Okay, if you are a math-like student, okay, who hasn't had 214, come and talk to me before you take the class. Okay, talk to me right after class here, because it's important that that's important material for what we're going to be doing in here. We're then going to spend some time using sorting as an example of an algorithm problem. We're going to go through the classic sorting algorithms. We're going to go through them in an analytical way. So we talk about, some of the ideas that they have for other algorithm design problems. Okay? And then we're going to have the first midterm. After that, we're going to begin a 3-week unit on graph algorithms. Here's where things like we were talking about shortest path algorithms a few minutes ago. This is where we'll talk about shortest paths and minimum spanning trees. And so if you don't know what any of that stuff is, don't worry about that. But that's where we're going to talk about those kind of algorithms. Breadth first search, depth first search, things like that. After that, we're going to talk about backtracking, exhaustive search techniques. We've seen that with this traveling salesman problem, the only program for actually doing it is going to have to basically search through all possibilities. But there's a big difference between searching through all possibilities in a clever way and searching through all possibilities in a stupid way. And that is where we're going to have our homework for the programming contest thing. You will be given a problem. You will be asked to write a backtracking solution. And the fastest programs in here are going to be many thousands of times faster than the slowest ones. Okay? And I look forward to seeing that happen. After that, we're going to talk about things related to a algorithm technique called dynamic programming, which is very useful on algorithms related to text strings and things like that. And that's a very, very powerful technique for giving optimal answers to things that are efficient in ways that wouldn't seem otherwise possible. That's what we're going to talk about and then we're going to have midterm 2. After the second midterm, we're going to talk about problems for which there are no fast algorithms. We're going to start to talk about this notion of computational intractability, NP-completeness, and things like that. And that's usually things people find interesting. Then we have the final exam, and that's people find even more interesting. Any questions about what we're going to do in here this semester? Okay? Fair enough. Okay? Any questions about traveling salesmen before I move on here? Okay? Good. So we're going to talk in here about efficiency. And again, sometimes, not often, but sometimes when I talk about a problem like the traveling salesman, and I say there's no fast algorithms, there's some student in the back who'll start snickering. He says, yeah, I got my daddy has a supercomputer, and he has 1,000 cores on it, and he can make anything fast. Okay? And the answer is no. Okay? We're going to see here in this course, again, we're going to talk starting next class about the big O notation and how we measure the efficiency of algorithms. It's an interesting property that fast algorithms, okay, on slow computers eventually always beat slow algorithms on fast computers, okay? And so there's a lot to be gained in being able to design fast algorithms, okay? And all this talk about big data and cloud computing and all this kind of stuff doesn't mean it make any difference, okay? In fact, who is it in the world that has the most computer power at their disposal? Anybody want to take a guess? You say the military? I think I know who has even more. I don't know, but who would I guess has probably even more computer power than that? Okay, who? Okay, IBM. I'd say Google if I was making a guess now, right? Google has zillions of computers. And one thing that I'm very proud of is actually if you go to Google and they say, what book should you read to prepare for your Google interviews? It's this one, okay? Because when they try to hire people to work with these zillions of computers, what do you do with them? Is it that they say, ha, 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 efficiency doesn't matter because I've got a zillion computers? Or do they say, my God, I'm working on such a big computation, I really need to be able to do it right? That's what they say, okay? Any questions about that? Okay, fair enough. So that one we shouldn't be debating anymore. Now, on the homeworks, you guys are going to be asked to turn in descriptions of algorithms. And one thing that we should talk about now, before you actually try to write up any algorithms, is how is it that you should describe them? Okay, an algorithm is the idea behind a computer program. One way to describe an algorithm is to write a computer program of it, okay? If I said, here is an algorithm on the homework, and you went off and wrote a Python program that implemented your algorithm, right? And you turn in the Python program, assuming your program is right, you did very well, right? But it is very, very difficult to get all the details right in a program, okay? And so when we talk about describing the algorithms in here, we are usually going to describe them not by complete programs, but in one of two ways, either in English, okay, as a little written description of an idea, or in something like pseudocode, a programming language that you sort of make up as you go along, okay, describing the basic steps of what you're doing, okay? When I describe an algorithm, I usually describe the ideas of an algorithm in English. What is it that I'm trying to do? And then I will write out a pseudo-programming language-like thing to carefully describe the steps at the level of detail that's necessary to see what's really going on. So if you take a look, for example, going back to the beginning over here, what was my description of the nearest neighbor algorithm for traveling salesmen? At the beginning, if you look at it in the red, I described it in English, right? What was my idea? My idea was start at one point and visit everything successively from there, right? Constantly trying the closest point possible, okay? What I have in the black is pseudocode. It sort of looks like a programming language, but it doesn't compile. But on the other hand, it probably resolves certain details here, okay, that maybe are left undiscussed in the big English description. When you're describing algorithm problems in here, what I strongly encourage you to do is to write out what your idea is in English, okay? An algorithm is based on an idea. If you don't have an idea, you probably don't have an algorithm. Does that make sense? So describe basically what your idea is in English. If there are tricky things and there's details you need to clarify, then I recommend you use some kind of a pseudocode notation, okay? But what I hate seeing on exams is I will say a problem, it'll say design an algorithm for this, and suddenly I see large pages of people writing broken programming-like language-like code without any description of an idea, without any picture of what they're doing, okay? Many of these ideas are best expressed by pictures, okay? Make sure you express the idea in English and go to pseudocode only if you need more details. Any questions about that? Okay, so that's what I mean by in expressing algorithms. Okay? Any questions? If so, what I think I'd like to do for the rest of the class is I have another one of these algorithm problems I'd like us to sort of think about a little bit. Okay? This is a problem about scheduling. In particular, scheduling for movie stars. Suppose you are a movie star, or perhaps more likely the agent for a movie star. Okay? And they have a bunch of different movies, projects that are competing for them. Okay? Let's say you represent Brad Pitt. A lot of people want Brad Pitt to appear in their movie, right? Every movie project is going to start at a particular date, meaning they want to start filming on a particular date, and it's going to go on for a certain number of weeks. Does everybody kind of get that idea? So what I want to claim is the amount of time you block out for something on a schedule. Okay, let's think about it. I guess I'm trying to think of schedules like this. Think of a picture where there's a flow of time on the x-axis. Okay? This is the beginning of the year. This is the end of the year, right? For every possible project you can do, there is a start date to work on it and an end date to work on it, right? So if you look at one of my books, let's say, which book? Let's say they wanted to make a movie out of programming challenges, my programming challenges book, right? They're going to start filming it on this date and end it on that date. Does everybody see that? So for every project that requires a continuous block of time, we can represent it by a line segment on this interval. How many people are with me at this point? Who's confused? Any questions about it? Now, the problem with this, of course, is Brad Pitt can't simultaneously work on programming challenges and the 4-volume problem. Why? Because both of those films are filming at the same time period, right? And his attention is required for one of these jobs continually. So suppose these are a set of possible movies, and suppose every movie pays the same amount. What is the right set of movies for Brad Pitt to be working on? Okay, if we look at these particular things. Somebody else have an idea? Yeah. Wait, which one you want me to work on? Which one? This one, discrete mathematics? Yeah. Which one is it? You want this one? This one you want? Wait, which one do you want? This one or this one? This one. You want Steiner's tree, okay? You want him to do programming challenges. Calculated bets, okay? That way he could do 4 movies. Does everybody see that? Okay? Is there any way he could do 5 movies? Okay? I don't believe that there is a way to do 5 movies. Okay? Here. Okay? Notice that if he picked some other movies, he'd be in trouble. If he started doing Tarzan of the Jungle, okay? Then I guess if he picked that one, there's no way to do, he couldn't do any of these other ones, right? And then he'd be stuck, I guess he could only get 3 movies done, right? So what is the schedule? Yes, question. You're being paid per movie, not per hour, okay? So you're getting paid, in this case, we want it. What is our problem here? Okay, the movie star scheduling problem, okay? It says that we are given as input n intervals, one interval for each movie. And we want to know what is the largest number of movies, the largest subset of intervals, such that we can pick such that no 2 of the movies overlap, okay? Because we're getting paid the same amount for every movie. We don't get credit for working on a long movie or a short movie, okay? But we want to get the most movies possibly done, okay? How many people understand the problem? Okay, any ideas for an algorithm about that? Okay, let's say yes. Okay, so what you're suggesting now actually is an interesting idea. You're suggesting that we take something and take figure out which movie is going to prevent him from doing the most other tasks. Okay? Is that kind of what we're sort of saying? So on this particular example here, which movie would be a terrible movie for him to wait, you want him to pick the movie that will interfere with the fewest number of other movies. Okay, let's think about that. Which movie will interfere with the fewest number of movies? Calculated bets. Okay, and so you would say take calculated bets, right? Then you would probably drop this and that from there. What would be the next movie that you would pick? Okay. Any idea? Okay. People see what the idea. What would be the next movie that you would pick? Now, at that point, programming challenges only intersects one more, right? And then that would be, now we've got those two. Oh, I guess this did, right? So this wouldn't intersect anybody. You get that one for free now, right? Okay. Let's keep going now. Now, what would be the one that intersects the fewest? Okay. It looks to me like Steiner's tree sort of does, right? Oh, wait, no. Is Steiner's tree one? It would, okay. And that seems to, that then if you pick that one, then when that would blow away this, you'd be left with this and this, and picking either of those would give you 4, right? So it looks like on this example, your heuristic of picking your strategy of picking the one with the fewest number wins, right? What about you? Okay?
I was going to say that with discrete mathematics, take up the next fewest after Steiner's tree, but you're already.
Okay, it's hard for me to do these things in my head, but let's think about what the algorithm is. Everybody get the idea of what the algorithm is? Find which movie is it that that intersects the fewest number of other movies, okay, and use that one, okay, because that way you're blocking the fewest number of other jobs, right? How many people think this gives you the fewest number of movies? Let's you, Brad Pitt, do the most number of distinct movies. How many people think this is a correct algorithm? Raise your hand. How many people think this is an incorrect algorithm? Raise your hand. Okay, a few more. How many people didn't think? Okay, a large number, right? Let's figure it out. How would we know this? Either you need to prove this is right, or you need to come up with a counterexample. What is a counterexample? Okay, a counterexample is an instance where that algorithm does the wrong thing. Okay? Can anybody come up with an example, a set of movies, for which always picking the one with lowest weight, okay, does the wrong thing? Yeah? Well, what if you have two movies that are both of the same length? That, in principle, should be, picking either of them should be. Oh, wait, so what you're saying is, how do you break ties in a decision like that? And often the devil is in the ties. My instinct, he's going to say, he doesn't care about ties, okay? Whenever you have two movies, the one that intersects the fewest movies, that's the right thing to do, okay? Can anybody come up with a counterexample to this? Let's think about it, okay? It's not one of the ones, I think, it's funny, I think I happen to have worked this one out. Let me just think about this. Okay? Let's look at this example here. What is, right now I've got 9 segments here, okay? What is the most number of movies that I could work on this without any interference? Yeah? 5. And which ones are they? The red ones. Does everybody see that? Okay? And I could pick these 5 red ones, and that would be just fine, right? What would happen, though, if I use your heuristic? Okay? Now, what do you pick the one that interferes with the fewest other movies, right? So what would that heuristic do now? First blue one, and the first one intersects 2. This one intersects 1, right? You would say, I'll pick this one, right? And then that would go away, and then you'd pick this one. It would do the exact right thing, right? So your heuristic looks pretty good. But what if I go ka-chunk, 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 ka-chunk? Okay? Now let's look at this thing, okay? Now it's going to say, I want one, the one that intersects the fewest is one that only intersects 2 other movies, right? And which is one that intersects only 2 other movies? The red one in the middle or the blue one. Which is the right one to use? Who knows? But if you're like me, if you have a choice of 2 things, if you pick heads or tails, I picked the wrong one, right? Okay? So does everybody see that now your heuristic, now your thing is relegated to your heuristic? It's not an algorithm, right? Because if you pick this one, you're doomed to not being able to get 5 of them, right? Does everybody see this? The act of algorithm design, a big important thing is learning to look for counterexamples, okay? And that a lot of ideas for what makes a good algorithm looks good until you think deeply about it, okay? Yes? Why don't we use by contraposition? Oh, you're trying to say, why don't I prove it's correct? You want to now say, why don't I come up with a proof of correctness of an algorithm? Proving the correctness of an algorithm is an important thing, but you need something to start with. You need a correct algorithm to prove it's correct. Does that make sense? If he had started out and I said, write a proof of your algorithm, I'm quite convinced he could write a proof of his algorithm. It would have been long and complicated and messy, okay? And it would have been wrong. There's such a thing as a wrong proof, okay? So what I say when I'm thinking about algorithms, the first thing that I do is I try to come up with an algorithm. My next thing is I try to think of why might it be wrong. That's a counterexample. And this is one that is a good thing to do. Because given this, his belief in his algorithm crumbled rapidly, right? If he came to me with a 3-page proof of the correctness of his algorithm, I wouldn't believe it that much more, right? Because proofs can be messy and complicated. Proofs are important, and I'm not trying to tell you they're not, and obviously we're going to do some in here, okay? But recognize that you should always be looking at algorithms with suspicion, okay? Looking for counterexamples, okay? Trying to prove them wrong. And when you can't prove it wrong, that is when you start to try to prove it right. Any questions about that? Yes? Is there an answer? Yes, there is an answer to this thing. And given the, let me actually show you an answer for it. Again, we've gone through this in a lecture in a little different order than I usually like to do it. There are a couple of other ideas people come up ahead of this that's often wrong. But what about this algorithm? This algorithm is the first to complete job, okay? Basically, look at the movies from left to right and figure out which movie ended first, okay? Then take that job, okay, and keep repeating. So let's go back to this example over here. Let's go back to the original input here. Which was the movie that ended first, going from left to right? Discrete mathematics, right? Suppose we pick discrete mathematics as our first job. Is it possible we have done something wrong here? Now we need a proof, right? I argue that if you pick the first movie to end, that has to be, will lead you to a correct solution. Why is that? Can anybody argue that that's a good thing to do? Yeah? So let's look at this thing. My first movie is going to have to end someplace, right? Let's say I look at my optimal solution. My leftmost movie is going to have to end someplace, right? Could I have possibly been better off taking this book, movie, The President's Algorist, ahead of discrete math? No. If that's my first movie to end, note that this one can only interfere with more subsequent movies than this one can. Does everybody see this? In an optimal solution, there is going to be a leftmost movie you pick. Brad Pitt is going to ultimately have a first movie he works on this year. The one that ends quickest has the property that it will interfere with the fewest other movies to the right of it than that one does. Correct? So there's no reason why you are better off picking any of the other ones that intersect this than the first one to complete. And is there any reason why you might not want to pick any of these three movies? See, all these movies intersect discrete mathematics, right? Is there any reason why the optimal solution might not pick any of them? Well, no. Because by definition, if you don't pick one of the ones that intersected these, if this was your leftmost movie, you could have picked one of the other ones that started earlier and made your solution better. Okay? How many people are convinced that picking the leftmost movie to stop first is correct? Okay, how many people are still a little wishy-washy on that? Okay, any questions about that? Okay, yes? I could alternately, if I wanted instead to read from right to left, okay, and some languages people read from right to left in, right? If I had lived like that, I could have made the same argument. Pick start from the right and take the first movie to begin, okay? And that's the same basic algorithm. Does everybody see that? Okay? And the same basic correctness argument. So the interesting thing here is we have an algorithm problem where there is a fast algorithm, where there is a clever thing, and it's not that complicated, right? Okay? And the way that you figure these things out is you think about ideas. You think looking for counterexamples. Why might this be wrong? Then once you've gotten a little bit of confidence on it, then you start thinking about why it might be right. Okay? And that's what a proof is about. A proof is a statement about why it might be right. Okay? And the reason here is now there's sort of a proof by contradiction. You were mumbling about proof of contradiction a little earlier, right? Now you can give a proof by contradiction that this is right. Suppose it is wrong. Suppose that picking this thing did not lead to the right answer. Well, then you show the contradiction, and that's the proof. That's basically the argument that I was giving. Okay? Any questions about that? Okay? Any other questions about this or any other things? Okay, about these kind of scheduling problems? This semester, we're going to look at a bunch of algorithm problems. Our goal is to learn how to separate the ones that don't have fast solutions, like traveling salesman, from the ones that do, like the movie star problem. Okay? And that is what we're going to talk about. Yes? Okay, sit down for another second. We're going to keep going till exactly 2:20. So, yes. What's your question? Okay, so this has to do with a lot. This is the case of optimization problems. There is usually a proof of whether your algorithm is right or not. It's important that you learn how to give them. Let's talk about that now after class. Okay? Thanks a lot. See you guys next time.
I just want to ask them whether Friday time would, if it would resolve the conflict.
Which is better for you? No. Okay.
No?